So, today we shall consider some more examples of a Turing machine. A Turing machine has an infinite tape and it has some non-blank portion, rest of the tape is blank. I use this symbol for blank. In the last lecture we considered them as an input output device. Today also first problem we will consider it as an input output device. So, when you start the machine in an initial state, say q naught, you have to specify the head position. This is called the head of the Turing machine, head of the tape. There is some non-blank portion, that is the input. After making some moves, the machine halts, and when it halts, whatever is the non-blank portion, that is the output. Okay. We considered two examples in the last lecture. One was to check whether a binary string has odd parity or even parity, number of ones is even or odd. Another one is whether a given string of parenthesis is well formed or not. Today we shall consider an example where a unary number will be converted into a binary number. So, the input is given like this is the tape. Suppose I have 1 1 1. I have 9 ones, it is a number 9 in unary. It is padded with some A, or you can just have blank also, does not matter, blank itself is okay. So, the input is the number 9. In this example I am taking any n, number n will be given as a unary number 3 4 5 6 7 9. What is the binary equivalent to 9? 1 0 0 1. I want to get this, but I should not mix up with this one and this one. So, rather I will print it as B A B, where B has the representation 1, A represents 0. So, at the end I should have B A B printed here in this portion. These ones you can change them to X's at that time. So, when the machine halts, whatever you have here, you must interpret the B as a 1 and the A as a 0, and this should give the binary representation of this unary number. How will you design the machine? How will you design the Turing machine? Now, how do you convert a binary number to a unary number? Suppose I have 9, you divide by 2, quotient is 4, remainder is 1, again divide by 2, quotient 2, remainder 0, then divide by 2, quotient is 1, remainder is 0, divide by 2, 1 0 1 1. This is, you know, so the representation is 1 0 0 1, this you should get. So, what you do is, informal description we can very easily give, but it is also necessary for us to give the formal definition, that is the delta mappings. Informally you can very easily describe this. Change the alternate ones into X's, and while doing switch between q naught and q1, 2 states, q naught q1 q naught q1, like that you switch. So, if you are in Q naught, that means you have seen an odd number of even number of ones. If you are in Q1, that means you have seen an odd number of ones. So, when you reach here in Q naught, that means the remainder is 0. If you reach here in Q1, that means the remainder is 1 when divided by 2. Go back and depending upon what is the remainder, print B or A. Then now I have 9 divided by 2, I have 4 now. These have been changed to x's. I have 1, 2, 3, 4 now, right. The quotient is there as ones, right. Change alternate ones, change this into x, leave this out, change this into x, leave this out. Then when you reach here, you will realize by going in state Q naught that you have seen an even number of ones, the remainder is 0. Okay. So, go back and print a 0. Again do the same thing, change this into x, leave this out, go print a, right. Then again do the same thing, leave this and change this and go and print a b. Now, when you go, you do not see a 1 at all, you halt. So, at this stage the output is given here, right. So, the input is a string of ones, is not it? Input is a string of ones, it represents a unary number. So, you start in state Q naught, delta of, the mappings will be written like this, maybe I will write here, delta of Q naught 1 is Q1 x r. The mapping depends upon the state and the symbol read. Depending upon the state and the symbol read, see when you have a symbol A and you are reading this in state Q, the mapping will be given by delta of Q A is equal to some P A R or L. That is, the state will change to P, from Q it will change to P. Over this A, the symbol will be printed and the move will be, tape head will move here if it is R, it will move here if it is L. In fact, in some books you also use stationary, remaining stationary also is used, but that is not, many books you will say only L and R. The reason is remaining stationary you can achieve by 2 moves moving left and right. So, usually only L and R are taken into account. So, in Q naught you see a 1, change this into a x and move right in state Q1. Now, alternate ones you have to leave out, okay. That is, you should not change it into a x. So, delta of Q1 1 is, but the state should change. See, between alternating between Q naught and Q1, you are remembering whether you have come across odd number of ones or even number of ones. So, state goes to Q naught, but this one you do not do anything with that and you are moving right. So, next instance it will be Q naught and 1, right. What is the move for Q naught and 1? Q naught 1 is Q1 x r. So, change this into a x and move right in Q1. In Q1 when you see a 1, you leave the 1 out, but change the state to Q naught. So, next instance you will go here in state Q naught and in Q naught if you see a 1, you go to Q1, print a x and move right. So, print a x and move right in Q1. In Q1 if you see a 1, go to Q naught, but do not do anything with the 1. So, you will move here in Q naught. Q naught 1 is change this into x and move here in Q1. Q1 1 is just move right in Q naught. Q naught 1 is Q1 XR. So, this will be changed into x and you are here in state Q1. So, the first blank symbol if you see in Q naught, it means you have come across even number of ones. If you see the first blank symbol in state Q1, that means you have come across odd number of ones. So, when divided by 2, the last digit will be 1, I mean the remainder is 1. So, that is in the binary representation the last digit will be a 1, right. We have assumed that B stands for 1 and A stands for 0. Now, it has to move left, come across all this x's etc. until it reaches the B. So, delta of Q1 blank is Q3, right. Then blank, it does not do anything with the blank symbol, just blank, starts moving left. So, in state Q3, it starts moving left until it sees a blank symbol. So, delta of Q3, here it can be anything except blank. So, I will put it as some z equal to Q3 ZL. Now, z can be, it can be x, it can be 1, it can be A, it can be B, anything it can be except blank, because after some time you will also have A, B's here. It will move through all this, and in Q3 when it sees a blank, it goes to a state Q4 and what will it print? What will it print, B or A? Q1 means it has come across odd number of ones, that means it what it should print, B. Louder please, you can, B. And in Q4 it starts moving. So, in Q3 it has moved completely over this, and here it prints a B and moves right in Q4. In Q4, see the x's, it has to cross some x's, okay. In Q4 it will move right, and when it sees the first one it will change, it starts changes the second. The second step will be, second pass will be started. So, delta of Q4 x, or not even x, it again I will put it as some y, will be Q4 yr, but when it is, what is y? Y could be a x or a or a b. Now, delta of Q4 1, it has to start the process all over again. So, when it comes here in state Q4, when it sees a 1, it will change this into a x and go to Q1 x r. Now, in Q1 it has to pass through the x's, delta of Q1 x is equal to Q1 x r, but when it sees a 1, it goes to Q naught, right. So, it goes to Q naught. In Q naught, if it sees a x also, Q naught x is Q naught x r, it will just move right. So, here when it comes, it will change this into a x, move here in Q1, then move here in Q1, then move here in Q naught. Is this clear? It changes alternate ones into x's and also switches the state from Q naught to Q1 and so on. When it passes over the x's, it just moves right, whatever state it is, either Q1 or Q naught, it just moves over. So, ultimately when it reaches the here it is Q naught, so it will reach the blank symbol in state Q naught. That means it has come across even number of ones. So, in Q naught it sees a blank. So, delta of Q naught blank. Now, what state it has to go? Not Q3. Q3 if it moves left, it prints a B. You should have a state for printing a A. So, it goes to say Q2 blank L. So, here it moves here in state Q2, and Q2 it just whatever symbol is there, it moves left until it reaches the blank. So, similar to this move, Q2 Z, Z can be anything. I will write Z here. Z belongs to X, what is that? X1 AB. Now, instead of Q3, if you have Q2, Q2 Z is Q2 ZL. So, you have reached the blank symbol in Q2. Now, what should you print? A or B? A. So, delta of Q2 blank is Q4A, right. So, you print a A and move right in Q4. In Q4, you move right until you see a 1. In Q4, you see a 1. When you see a 1, you change that into X and move to Q1. So, you change this into a X and move right in Q1. In Q1, you go up to this, just move right, and when in Q1 you see a 1, you go to Q naught, do not do anything with the 1, move right. So, you go here in Q naught, then you move right in Q naught. Now, in Q naught you see a blank symbol. What does that mean? You have come across even number of ones. So, the remainder is 0. So, you go to Q2, Q naught blank is Q2 blank L. So, you start moving left in Q2. you move left until to this blank. And in Q2 blank you have to print a and move right. So, print a here and start moving right in Q4. In Q4 you start moving right until you see a 1. Right. When you see a 1, you go to Q1, make it a x and move right. So, make this into a x and move right in state Q0. Q1. So, in Q1 you see the blank symbol, here you move in state Q1, and Q1 blank is you have to move left in state Q3. Say in state Q3 you move left until you reach this blank. In that case you print a B and start moving right in Q4, right. In Q4 when you see the first one, you change this into a x and move to Q1, right. Now there are no more ones left, right. So, you will be moving right in Q4 throughout and reach the blank symbol in Q4. So, when you have Q4 and a blank, halt. Blank again you do not do anything with the blank. You go to the halting state and halt. Usually after the work is done, you go to a halting state and that is denoted as H. You do not make, usually after that is over, the machine halts. After the computation is over, the machine halts, right. So, now all the ones have been changed into x and you have the binary representation of the number. This is a unary to binary converter. Okay. So, by practice you should be able to write this moves. So, we will take, I will give some assignment with a number of problems. So, now if you suppose I have 6, how will it work? It will first, if I have 6, then it will change the first one into x, leave this out, change this, leave this out. When it goes to the blank symbol, it realizes that it has come across even number of 1. So, comes back in state Q2 and prints a Then next step it will change this into x, leave this out, change this into x. That means it has come across odd number of ones in Q1, it will reach here in Q1, come back in Q3 and print a B. Again go here, now change this into x, it will reach here in state Q1, come back in Q3 and print a B. This is the way it works. Thus, we have seen that we can have a Turing machine which converts a unary number to a binary number, and it has got 5 states. Q0, Q1, Q4 are right moving and Q2 and Q3 are left moving states. These are the mappings, this we have seen just now. Let us see how the machine works on another tape having 5 ones. This number 5 has to be written in binary in this place. So, initially the machine is reading this 1 in state Q0 and uses this mapping Q0 1 is equal to Q1 XR and goes to the right, printing a x on the cell it read. Now, from this situation it leaves out the next one and goes to the next cell, just reads it and moves right using this mapping. Now, in Q0 again it sees a 1, it changes that into a x using this mapping and moves right. So, it changes alternate ones into x's and leaving the other ones as they are. Now, in q1 it sees a 1, it moves right in state q naught, but does not change the 1. The last symbol it reads is a 1, it reads it in q naught and using the mapping q naught 1, delta of q naught 1 is equal to q 1 x r, it changes that into x and moves right. Now, it sees the blank in state q 1, that means it has encountered an odd number of 1s. So, it moves back and then it has to print a B here, that is B denotes a capital B denotes a 1 and A denotes a 0 here. So, it has to move left and print a B in this position. So, in q1 B it moves left and it uses this mapping q1 blank is equal to q3 blank L and moves left in state q3 until it reaches here, and in this position it reads the blank symbol in q3 and it uses this mapping delta of q3 blank is equal to q4 blank R, prints the capital B here and moves right in state q4. q4 it moves right, it is a right moving state, it moves right in state q4 till it sees a 1. So, this x it does not change and it just moves right. So, in q4 it reads a x, it just moves right going to the next symbol 1. Now, in q4 it sees a 1, this is the situation, and it uses this mapping q4 1 is equal to q1 x r and moves right. Here again there are two ones, it changes alternate ones into x's. So, this one it changes into x, but this one it leaves out, moves right, uses this mapping, moves right, but does not change this one and again moves right, and in this position it reaches x in state q naught and delta of q naught x is equal to q naught x r, uses this move and goes to the blank. Now, in this position it reads the blank in state q naught, that means it has encountered an even number of 1s. So, it moves left in state q 2 and when it reaches the blank cell here it prints a denoting a 0. So, in this position it just starts moving left and the state is q 2 now, it moves and at this position it prints a and moves right. In q 4 it just moves right and when it encounters the first one it changes that into a x by this move, delta of q 4 1 is equal to q 1 x r and goes to the next cell. It reaches the blank in state q 1, again that means it has encountered an odd number of 1s and starts moving left in state q 3. It moves left in state q 3 until it reaches this blank, it prints a B and starts moving right in q 4. Now, we have the binary representation of 5 here BAB, and in q 4 it moves right looking for the next one to change, but it does not encounter a 1. There is no 1 here, all the ones have been changed to x. So, it reaches the blank symbol in q 4, that means it has converted all the ones into x's and the process is over. So, it halts at this position. In q 4 when it sees a blank it halts, at that time the output is BAB, of course followed by some x's, but the output you are expected to have is in terms of BA and B standing for 1, A standing for 0, and it gives the binary number 5. So, this is the way the unary to binary converter works. Now, the same problem, same input, same output in the same position, same work, I mean I would not say same working, the input is same, the output is also B and A and the same position, do it with 2 states. Now, how many states we have used here? Q0, Q1, Q2, Q3, Q4, 5 states I have used, and you must realize that Q0 is a right moving state, Q1 is a right moving state, Q2 and Q3 are left moving states. When you go to Q2, you move left. When you go to Q3, you start moving left. When you go to Q0, you start moving. Q1 is right moving, Q4 is also right moving. So, out of the 5 states, Q0, Q1, Q2, Q3, Q4, this is right moving, this is right moving, this is left moving, this is right moving, right, is not it so? Now, achieve the same effect with 2 states, same input, output, do it with 2 states. The number 9 is given. Or maybe I will blank, blank. Ultimately, I want BAAB here, right. The machine starts here in state Q0. So, delta of Q0 1 is Q1 XL. You are going to have this number by using it as a binary counter. Initially, you will have 1, then increase it to 2, 3 and so on. So, first when it sees a 1, it changes that into a X, moves right in Q1. In Q1, now it has seen 1, 1, right. So, it has to print a 1, that is A, right. So, delta of Q1 blank is Q0 A right. So, it prints a and it prints a B, prints a B, B is 1. So, it prints a B and moves right. B is 1 and A is 0, B is 1, A is 0. Now, now you have 2 states. So, one must be a right moving state, another must be a left moving state. So, in Q0, when you see a X, you just move right. Then when you see a 1 in Q0, change this into a X and start moving left in Q1. So, in Q1, if you see a X, just move left. Now, in Q1, when you see, now you have changed 2 of them into X's, now you should have the number 2, that is B and A you must have. So, when in Q1 you see a B, change this into a and move left, change this into a and move left. In Q1 when you see a blank, print a B and move right. So, now you print a B and start moving right in Q0. Okay. So, now you have changed 2 of them into X's and the number 2 is appearing here in binary. So, move like this. In Q0 you change this into a x, come back in Q1. In Q1 when you see a, number 3 should appear here, that is B should appear here. So, A will be changed into a B, Q0 B, right. You will start moving in Q0. In Q0 you move over the x's and come here. Q0 1 is Q1 XL. So, you change this into a x, move, then in Q1 when you see a B, change this into a, move left, again when you see a B, change this into a, move left, when you see a blank, print a B. Now, 4 of the ones you have converted into x and you are having the number 4. Now, do the same thing, change this into a x and come back here, you will be seeing a, right. Then you go to Q0, print a B, move right, change this into a x. In Q0 you move right, in Q1 you move left. Q1 you come here, when you see a B, change this into a, move left, then when you see a, change this into a B. Now, I have number 6, 110 I have, BBA is 110. Now, again move here, change this into x, come back in state Q1, change this A into a B, 7 I have now, go change this into x and when you come back, change this B into a, move left, change this B into a, change this B into a, then when you see the blank, print a B. Again go, change this, come back, change this into a B. Now, in Q0 if you are supposed to see a 1, delta of Q0 blank you halt. Let us see how this works on the unary number 5. We have this situation 5 ones and it makes use of the move delta of Q0 1 is Q1 XL. Q0 is a right moving state and Q1 is a left moving state. Using this move it becomes like this. Now, in Q1 when it sees a blank it prints a 1 that is B and moves right. It uses this mapping, prints a B and moves right in state Q0. Q0 is a right moving state, it moves over the x's and when it first sees the 1 in this situation, it converts that into a x and starts moving left. Now, 1 has been changed into x and you have the number 1 here, B denotes 1. When you change the 1 into a x, you have to move left and have the number 2 here, that is BA you must have. Let us see how it happens. In Q0 1 it changes the 1 into x and moves left. In Q1 it sees the x again moves left using this mapping, and when it sees the capital B in state Q1 it changes this into a using this mapping and moves left. So, it prints a B here using this move, prints a B and starts moving right. In state Q0 it goes over everything and changes the next one into a x and starts moving left. It proceeds like this. At this situation it has converted 4 ones into a x and you have the number 4 here. The tape head points to the last one, it is seeing the one in state q naught, it changes that into x and start moving left in state q1. Now you have the number 4 here, when it sees the a in state q1, it changes that into a b and starts moving right. It uses this move delta of q1a is equal to q1br, changes that into a b and starts moving right. Now in q naught it looks for a 1, but it does not get a 1, it keeps on moving to the right until it sees the blank in q naught. At this stage it should be understood that it has converted all the ones into x's and so it halts. So, the number 5 is again here the output, the binary number for 5 is this, the unary number has been converted into the binary number. Note that in these two examples which converted the unary number to a binary number, the same problem is treated, but you are achieving the result in two different ways. Which is advantageous? Which one is advantageous to use? This one or the earlier one? The earlier one, the number of steps will be less. Even though you use 5 states, the number of passes you make will be less. Here the number of passes, each one you have to move right and so on. So, number of steps will be more here. That also matters. Okay. So, these are some examples of having the Turing machine as an input output device, right. So, you have now considered the unary to binary converter, construct a binary to unary converter, you can try that, or binary to decimal converter, whatever it is, something you can have, and you can multiply two numbers, you can add two numbers, all those things can be done. In fact, whatever you can do with for whatever you can write a program, you can do for this. But you must also realize that finite state automaton you can use for adding two numbers, arbitrarily large binary numbers you can use a finite state automaton. But you cannot use the finite state automaton to multiply two arbitrarily large binary numbers, right. Why? Because it has finite amount of memory. For example, suppose you can have a finite state automaton with n states for doing the multiplication, then consider some 2 power n plus 1 or something like that. It will be followed by 1 followed by some zeros, 1 followed by zeros, this will be the sort of input. You have to remember the partial product, that is not possible, right. So, at the end when you after getting 0 0 0 0 like that, it will get into a pattern, and when it reads a 1 1 it just cannot change and do something, right. The finite state automaton has only a finite amount of memory, but the whole computer system itself we can look at it as a finite state automaton, even though what it can do is see the number of each count the number of bits in the memory, number of bits in the registers. So, each bit can be a 0 or 1. So, I will just put it like this, in the main memory there are p bits, so many bytes then multiply by 8 or something like that, and the registers you have some q bits, then totally you have p plus q bits, each one can be 0 or 1. So, there will be the whole system, when you say it is in a state, there will be 2 power p plus q states. It is a very large number, you can look at it as a finite state automaton, but that number of states is extremely large, and when something takes place it changes from one state to another, right. And what sort of a program will have the maximum possible running time on such a computer, just for curiosity? something which uses the main memory as a counter. Everything will be 0, 0, 0, 0, 0, 0, 0, 0, 1. Then increment by 1, you get 2, 3 like that. As a huge accumulator, if you like consider the whole memory, you will achieve all states, isn't it? The maximum possible running time you can have by achieving all states, right. So, and that sort of a thing will happen only when you look at it as a whole memory as a counter, keep 0, 0, then increment by 1 and so on. If you write a program that will that will have the, it will go through all the states if you look at it as a finite state automata. Otherwise anything will repeat without, see, you may have a program, it gets into an infinite loop or something like that, but then it will get into loop in such a way that it go back to the original state. It will not pass through all the states. When it wants, when you want it to pass through maximum number of states possible, you have to do like this. Consider it as a gigantic accumulator and keep on having the numbers. Now, Turing machine as an acceptor. We look at the Turing machine as an acceptor. It accepts some strings. Okay. Type 0 languages or recursively enumerable sets are accepted by Turing machines. It accepts type 0 languages. They are also called recursively enumerable set. Now, when you define a Turing machine as an acceptor, k sigma gamma q naught delta q naught sometimes this blank will not be denoted in the 7, I am taking it as a 7 tuple, sometimes it will also denoted as a 6 tuple in some books. We denote it like this. Now, when we look at it as an acceptor, the machine is taken like the tape is left end we are fixing now. It is infinite in one direction only now, because later on we will prove that two-way infinite is equivalent to one-way infinite. They are actually equivalent models, but when we look at it as an acceptor, we fix the left end, right end it is infinite. So, initially the input is given here followed by blanks. This is the input. The machine starts in the initial state reading the leftmost symbol. Here where the machine starts is fixed. When you look at it as an input output device, where it starts you have to specify. It is not necessary it should start at the leftmost non-blank symbol or something like that. You can start anywhere, you have to specify. But here the machine starts on the leftmost symbol and it keeps on moving in the same manner until it reaches a final state. When it reaches a final state without loss of generality, you can assume that it halts. So, when it reaches a final state, it will stop and accept the input. Okay. Here the thing is k is a finite set of states. Sigma is the set of input symbols input symbols, that is the input alphabet. Gamma is the tape alphabet. Sigma is contained in gamma. Blank belongs to gamma, but blank does not belong to sigma. Blank symbol is denoted like this. It is a symbol of gamma, but it is not a symbol of sigma. Delta we have to specify. Q naught in K is the initial state. F contained in K is the set of final states. Delta is a mapping from K into gamma into, tell me, depending on Q and the symbol read, the state is changed, new symbol is printed and it moves left or right. So, delta is a mapping from K into gamma into K into gamma into LR. This is deterministic. Please note that this is a deterministic version we are considering. We could also consider a non-deterministic version, right, that we shall see later. Okay. Next we have to define what is an ID and what is the relationship between IDs and so on, and what is the string accepted, how do you define the language accepted and so on. So, we shall continue in the next class.